Sounds good. Thanks, Mike. Go ahead and share my screen here and then jump into it. All right, nice to see everybody. For the next half hour or so, I'm going to give some updates about the Open Oximetry project, which I think everybody on this call has become familiar with in prior meetings. But for those who aren't, I will give a little bit of background on the project and try and highlight some of the key findings to date and where we are hoping to go next. Conflicts related to this to report. So just to give a quick overview of some of the big priority problems that are relevant to pulse oximetry that most people on this call are well familiar with. Access is at the top of the list, just access to safe devices. This is a huge problem worldwide. Digging in a little bit more specifically is the issue of performance and performance variability, not only with skin pigment variability, but the issue of low-cost devices in particular and variability we see there, and how regulation can potentially do more to try and address some of these problems. The last two pieces on here, the last two priority challenges rather that our project and others have been trying to address has to do with how to disseminate this performance data more transparently and in real time, as well as more material on education, how to properly use the devices. And finally, as Mike had alluded to, this notion that, fairly recently that problems with pulse oximetry performance were only recently linked to health and healthcare disparities. And we'll dig a little bit deeper into that. So most of that stuff is not new. The issues with variable performance in oximeters, this goes back 50 years. The modern pulse oximeter was introduced in the 1970s. This is Dr. Yagi in our lab, probably about 20 years ago. The first studies are really in the 80s that were highlighting this issue of variable performance based on skin pigmentation. In the late 80s, 90s, pulse oximetry started becoming more ubiquitous, standard of care. In the early 2000s, data in a more controlled way began showing this bias linked with skin pigment, but the bias was relatively small and at lower saturations and was thought perhaps not to be as significant as we're seeing that it is today. 2013, this is the US FDA regulatory guidance that incorporated some recommendations on how to ensure diversity of skin pigment in the testing cohorts, but that was really the first time that kind of was present in any regulatory guidance. And then in 2020, as Mike pointed out, this kind of landmark paper for the first time linked these performance differences that were being seen for decades with health and healthcare disparities. And this sort of sounded the alarm bells during COVID. The numbers at the bottom here give you a sense of the amount of data. Most of the data is coming from retrospective studies, hundreds of thousands of patients. There are a few small prospective studies, but very few. And just to highlight, most of the studies today are in high-income countries, predominantly lightly skinned populations. And that is something key to comment on just in terms of applicability of data. The last thing I'll point out in the last 5 years is not a surprise to anybody in this room, a huge explosion of devices coming onto the market that are low cost. This is a device for $1, basically, $1 US. I'll share some results later. Unsurprisingly, this device did not perform so well. Nonetheless, so with all that in mind, a lot of this was the impetus for the Open Oximetry project, which has a number of components that are shown here. A lot of what we're going to talk about today are updates from our testing of pulse oximeters. So we have a clinical trial, real-world, prospective, and critically ill adults, where we're trying to collect data on the performance of devices and understand what are the factors that are impacting performance in the real world. And then we do a lot of lab testing, and I'll provide some more background on that. Other components of the project that I'll allude to, the collaborative community, which most people on this call are already part of. This is trying to bring people together across different disciplines so that we can accelerate progress in this space. Creation of an open data repository, again, the goal to accelerate progress, and then working with regulatory agencies to try and improve standards and guidance. High level, these are some of the outputs from the project so far. We've shared, co-developed and shared a number of protocols for these types of studies. We've completed testing on 24 devices, and I'll go into that a little bit more detail later on. The real-world clinical trial has completed enrollment as of last week, so that's 620 enrollees in that trial. And then we've done 223 participants in the lab studies. The collaborative community has over 200 members at this point. We have released 6 publications, and we have about 9 publications that are in various stages, hopefully coming out in the next several months. And then have had about a dozen forum meetings of the collaborative community. So I'll touch briefly on some terminology for those who are not don't kind of live and breathe this stuff, no pun intended. But so on the left here, pulse oximeters come in many different shapes and sizes. They are integrated into wearables, phones, but fingertip devices, benchtop or tabletop devices, handheld devices, and multi-parameter devices. That's kind of what we're going to be mostly focused on when we're talking about devices today. They can be placed on all different parts of the body: the foot, hand, finger, forehead. And then when we're talking about types of probes, some shine light through the tissue, a transmittance probe, like through the finger. Others reflect light through tissue, a reflectance probe. So you might hear some of those terminologies. Fundamentally, you can kind of think of pulse oximeters in a very simplified manner as measuring the color of blood as a proxy for the amount of oxygen. So just like thinking back to like cartoons or a movie, people turn blue when they have low oxygen. The blood is changing color. You can see that in the syringes here. It's like a favorite game of anesthesiologists to like draw a blood sample and guess what the saturation is.
Which is the more saturated?
So the brighter the red, the more oxygen there is. The darker the blood, the less oxygen there is. The pulse oximeter is shining light into the tissue and trying to assess this kind of indirectly. The gold standard measure is this device on the right called a blood gas analyzer. You need a blood sample. Similar method, but it doesn't have the interference of the tissue. And so it can read the oxygen concentration of the hemoglobin in that blood more directly. So that's considered the gold standard. When we're talking about doing device testing, this is a picture of our lab in San Francisco and a subject with their hand with several devices under test on with dividers to prevent any kind of light interference. We call this a controlled desaturation study. Somebody sits on the kind of operating room table there, they breathe on a closed circuit, and we slowly desaturate them. We slowly lower the oxygen level in these 6 plateaus to try and get a distribution of samples across the range that's most clinically relevant. And then we compare the SpO2 from the pulse oximeter with the functional saturation SaO2 from the blood gas machine, and we see how close they are. Before we do that test, we are measuring a number of other parameters in the subjects, including skin pigment, a number of other demographics. And then during the study, we're measuring a number of physiologic characteristics, their blood pressure, their hemoglobin level, do they have anemia, things like that. Okay, so going back to some of these priorities, I'm going to focus in first on variable performance of devices, the issue of bias in people with darker skin pigment and poor performance of the low-cost devices. Before we were able to jump into testing lots of devices, one of the big problems that we needed to address was the issue of how to ensure diversity of skin pigment in the study cohorts. In that timeline, I had alluded to FDA guidance in 2013. It required this, which of the study cohort, at least 2 people need to have darkly pigmented skin. That is extremely vague. And it left the door open for a lot of freedom of interpretation of what that means. So the first thing that we started off doing was trying to figure out what the right method would be or what the optimal method would be. What we were looking for was something that was reproducible, that was not subject to operator bias, and that was based on some degree of population level data, global population level data, ideally, so that we're accounting for the range of skin pigments found around the world. One of the more common scales that was used until we began the project by our lab and several others was this Fitzpatrick scale. It literally looks like that, which does not look, I mean, you can kind of get a sense of how scientifically rigorous this scale was. It was not intended to be used as it was being used, but it was effectively how dark is the person in front of you on a scale of 1 to 10. But those colors are not standardized. Depending on what scale you download, it was a totally different scale, lab to lab, place to place. The Monk skin tone scale in the middle is another subjective skin tone measure. This was based on more population level data. It's a 10-point scale. The cutoff for Fitzpatrick was 5 and 6 were considered dark for Monk, HIJ. And then there are objective measures, these devices on the bottom that range from $100 to $15,000 or more per device. This is similar if you were matching, I'm told, foundation for makeup, or if you're going to the hardware store to match the paint color to your house. You want to be very precise. And this technology has been around for a long time. There are portable units, some of which are designed specifically for measuring skin pigment. And so we were deploying all of these methods and a handful of others that aren't on here and comparing what happens. What you can see on the left-hand chart is that depending on what method is being used, you may be falsely reassured that you have people in the cohort who have dark skin pigment. We saw that with Fitzpatrick scale. So with the Fitzpatrick scale on the right-hand side, to the right of that dotted line, it looks like we have a good proportion of the study cohort with dark skin pigment. But when we measure with a scale like Monk or the objective methods, we have a much lower proportion of people who actually have darker skin pigment. This was one problem that we had to get out of the way. So choosing the method was a big one for us. The other part of it is the definitions within these methods. What is the cutoff for dark skin pigment? On the left-hand side, this blue chart is the distribution of skin colors ranging from dark to light, measured with the objective skin color matching tool in our real-world clinical trial cohort. This is a trial in San Francisco. It's a predominantly light skin population. It is our public safety net hospital. It has a very diverse population, but at the same time, it is based in San Francisco. When we break out the darkest third of patients in our cohort, this is what it looks like when we're using the objective measurement. ITA, individual typology angle, not that important if you're not familiar with it, but again, it's this kind of quantitative assessment of skin pigment. -30 has been a proposed cutoff for this, but these data come largely from high-income country populations. They were diverse high-income country populations, but the data potentially have some limitations that we're hoping we can further refine. Dr. Bisagirawa, who is on the call, and Dr. Igaga, part of collaborators in the OpenOx project from the Association of Anesthesiologists of Uganda, are getting ready to start a project attempting to better characterize skin colors from around Africa. The study will be based in Uganda. Also, colleagues from Lightbox in South Asia are considering doing a similar study. We hope that we can introduce data that have been lacking in this space that could help kind of better define and ensure accounting for global populations. So once you have the right method, once you figure out the right cutoffs, another issue is how to use the method correctly. We do see with the subjective scales, inter-operator bias, imprecision, and for that reason, we think our recommendation and our practice has become to not only rely on the subjective scales. There are too many problems with them. Having said that, subjective scales are easy to understand, and it's a nice way to communicate. If I tell you, our study population has an ITA range of -30 to -50. Nobody knows what that means, certainly not consumers or clinicians. And so having the subjective scales is a nice tool that, with a grain of salt for the limitations that they have, if it's paired with an objective measure, we think that's sort of the best mix of objectivity, best way to ensure diversity, but also have a tool that can help communicate that to non-technical folks. The last piece that we had to figure out as well was this issue of race. Most of the studies that linked pulse oximeter bias tried to make the connection with darker skin pigment. We're using race as a surrogate for skin pigment. We have been using self-identified race as well as our skin pigment data to try and look at correlation. And the upshot is race really, as a social construct, it should not be used as a surrogate for skin pigment. Stating that in a slightly different way, for any given race, there's a very wide range of skin colors. And for any skin color category in any scale, there's also a wide range of races that will be represented in that. So to rely on that, there are, of course, linked at the extreme ends, it can be used slightly differently, but a big caveat. And so we've shifted away from using that to define the diversity of the cohorts, since skin pigment is really what we're focused on at this point. So how do the oximeters perform? We tried to look at devices that were most popular in global markets. So we feel like we've captured the majority of the world's global markets with an emphasis on devices that are more commonly found in low middle income countries. This basically is about 50 devices we have in the lab that we're testing on an ongoing basis. The price points range from that one that I showed earlier at $1.82 US to up to $8,000 per device. And these are, that's not a multi-parameter device, that is just a dedicated oximeter. We've done over 220 sessions. We are awaiting regulatory updates still for what the new standard will be. That is not out yet. We are trying to anticipate, and we continue to test and gather more data. And I'll share a little bit more about this in a slightly later session. But we've completed testing for our initial goal, which was to test 24 subjects per device. It is likely that we are going to end up needing to test 100 or more per device, just to put it into perspective, in order to power these studies. We're finding large variability in the device performance. Tech tier is very small. I don't label any devices, and I'll tell you why later. But what we're looking at here, each cluster of lines is a different device going from top to bottom in each of these columns. The devices that perform reasonably well are shown on the green box on the left for each chart, and those that cross over into the red zone, we had problems with. So about half of this is the first 24 devices that we're going to be releasing results on. About half of them.
Laser pointer doesn't work on the TV. Never mind.
Here, I'll use this.
Oh, there you go.
Yeah, so the devices over here, these all generally perform relatively well. You'll notice that the performance, I'm not going to get into the statistics of this because it's confusing. We'll talk about confusing stats in a little bit and why that's a problem with the Pulse Ox story, but this is root mean square error that we're reporting here, ARMS. You could think of it as kind of the accuracy, the measure of accuracy. And for each device, we break it up into dark, medium, and light skin groups, which are a bit hard to see on here. All the devices that are here on this left side that fall within the green bounds are less than the 4% ARMS currently required by ISO. Of note, current FDA is 3% for fingertip, and there's a good chance that 3% will be the direction that regulatory agencies are heading, but we'll hear from them in a bit. So if I were to draw a line right here, you'll see that quite a bit more devices would not actually be passing. And then all the devices over here are having problems, potentially more often in the cohorts with darker skin pigment, as indicated by these darker black lines. Another thing I want to draw your attention to is it's different by device. So not every device has a positive bias or a negative bias or the same magnitude of bias. And so that has been a challenge when we're trying to figure out how to power these studies, because the power for one device is not necessarily going to be the same as for the other. So again, I'm not going to go in more detail right now with the performance of the individual devices. In about an hour, we will go through a little bit more of that. So I'll put a pin in that for now. So in addition to testing the devices to try and quantify the magnitude, well, to try and figure out which ones perform well and which ones don't, and to try and quantify the magnitude of the bias that we're seeing that may be linked to dark skin pigment, the other thing we're trying to do is collect data so that we can better understand why the bias exists in the first place. What are reasons why that may be happening? One of the things that the project has spent quite a bit of time trying to do is create methods for capturing the raw signal that raw pulse oximeter signal, PPG, photoplethysmogram. It's kind of, you can think of it as like the waveform, which some of the devices display. But by the time you're seeing it as an end user, it's already been processed. The device has algorithms that will try and create this beautiful shape, but behind the scenes, it is using this raw data from the different wavelengths of light to try and understand and compute what the actual oxygen hemoglobin saturation is. On this figure on the right is a simplified diagram showing light coming. Think of it as like a transmittance probe, light coming through the tissue. It interacts with tissue. It also interacts with venous blood. The device needs to know, and I want to get rid of the venous blood. I really want to focus in on the pulsatile arterial blood signal. And so it's paying attention to the pulsatility here. The terms on here that you don't need to remember in about a minute from now, but will be relevant for the next minute. AC and DC, you can kind of think of like alternating current is a common way to refer to this, but the wave going up and down, and then you have the steady part of the signal, the DC component, and that's kind of always present and not moving as much. So So what we wanted to figure out was, are there clues in the raw waveform before it gets processed that could give us insights into why there might be different accuracy in different skin pigments? So we created a device to help us do this, which we've shared as open access for other researchers, and then have been collecting raw waveform data during all the tests where we're collecting data on the performance of the devices. And kind of spoiler alert, this is still very much underway. We are just getting the data set to a size where we can start to apply more advanced analytics to it. But roughly, we are one of the key findings so far, which I think for many of the researchers on the call may be unsurprising, but it has not been really described in the public domain as much as we would have thought. But we are seeing differences in the characteristics of this PPG waveform that are linked with skin pigment. So again, not totally an unsurprising finding, but we're excited to be starting to report some of this and get feedback from other folks that have been thinking about this for a long time. And also now we have a tool that hopefully we can use across different research teams to try and make progress on this. If you think about it like this, up until now, the raw PPG signal, this is heavily protected. Device manufacturers, this isn't something that people want to release for good reason, because they put a lot of time and IP into trying to figure out how to use this signal to come up with the number. And so we think this creation of this tool hopefully will be very useful to the collaborative community beyond. This is a picture of one of the devices that we've made and the raw signal coming out of it. Again, we're seeing links with skin pigment and the features of the waveforms. More data analysis needs to be done, but we also are seeing linkages with other factors, finger size, body mass index, other things that may also be playing a role in interacting with what we're trying to figure out here. BMI, finger size are one of probably 15 variables that we're collecting data on to try and figure out what are other possible interactions that may be happening here. Another is perfusion or pulsatility amplitude. Some devices report something called a perfusion index. They all refer to it as something slightly different. The way that this is calculated there is a relatively generic way that this is calculated. You can think of it as that AC signal, like how high is the peak on the AC signal over the DC signal? How good is that signal? How much pulsatility do I have in this signal? But the actual calculations are different by different manufacturers. So what we've tried to do is create a device where you can see what the math is, and we can compare apples to apples across different people, across different labs. So these were some data that we published in the last year, showing that in people with light skin is the left column, medium pigment and dark pigment, that as you move from right to left in any of these graphs, you see the noise start to increase. You see the bias start to increase. So this is going from high perfusion to low perfusion. Kind of think of it as going like the signal quality starts decreasing, although the factors that go into pulsatility amplitude are many more. It's a bit more complex than that. But what we saw was that perfusion is a big factor here. So one of the reasons this is relevant is when manufacturers are testing their devices for regulatory purposes, it is standard practice to induce high perfusion, to actually warm people's hands, to all sorts of methods deployed to actually make the perfect signal. And so how predictive, how relevant is laboratory testing of these devices for regulatory purposes when in the real world, that's not what they're subject to. And so we have been trying to tease that out a bit more. So here is similar data. These are newer data. I'm not naming the devices that are in here because we're just trying to talk about what the key takeaways here are, that we're seeing this effect across different devices without getting into the devices, but we see this in pretty much all the devices that we test. The two devices that have been tested in here, the top row and the bottom row, represent probably the majority of the world's global market. These are high-end devices that cost $3,000 each. So just to put that into perspective, these are newer data. This is the latest make and model for these companies, kind of their highest end units, we see a very similar finding. We just finished repeating this study in 114 subjects per device. So we're spending a lot of time trying to figure this piece out, and the raw PPG is going to be a key part of that. Other updates on progress in the project. Like I said, the lab is not the real world. Performance in the lab, to a certain degree, predicts the real world performance, but not perfectly. Some of the reasons are because of things like perfusion, but others are for reasons that we don't totally understand. These, as I mentioned, we just finished the real world clinical study at UCSF. We're doing adults. At Stanford, they're doing pediatrics. And there are a number of other clinical trials that are ongoing right now that are using similar protocols that we've tried to harmonize through the collaborative community so that we can pool data once folks have done their analyses, and we can pool that data to hopefully be able to answer these questions a little bit more robustly. We are hoping that in the next couple of months, we will be able to share the findings of that study. And again, we've been collecting all the same data that we're collecting in the lab in the real world clinical trial as well. So we're hoping that there'll be a lot of insights to come in the next couple of months. Beyond the lab studies in humans and the real clinical trials in humans, there are certain things we aren't going to be able to answer in those settings. And so we are looking at new methods, we and many other teams for that matter. One of the areas has to do with creating functional testers, simulators, phantoms. Some of these literally look like a fake finger. Some of them have real blood. Some of them are purely electrical. Trying to figure out if we can come up with a test that would predict to some degree poor performance of devices in the real world or in the lab. Very expensive to do the tests in humans, and in some scenarios, it's not safe to run all of the different conditions we want to simulate, or we can't do it in a very controlled way. And so that's where these testers come in. We've been collecting a lot of data that we hope to be releasing pretty soon. One of the big takeaways is these testers, they're a small number of testers that are on the market. They should not be used to validate the performance of an oximeter. We have seen those who are procuring devices or conducting research studies and justifying their decision to study a certain device. There have been justifications made based on, we used a functional tester, the device performed well, therefore it's safe to use in the real world. If they don't work that way, we now have some data that we've released, which is accessible through the website, that basically show that you can have a good device, a device that performs poorly in the real world look perfect on one of these functional testers. So we continue to do work to try and figure out if we can better predict that, but that's sort of our takeaway at this point, is just to use caution with these. We are hopeful that this will shed some insights into the issue of variable performance in skin pigment. Another method, kind of moving away from human studies, this is a method that Dr. Leo Shmulyevich at WashU, a member of the collaborating community and part of the OpenOx collaborators group, he has a model of a pig model where the pigs are engineered to have certain areas of skin with no melanin and other areas with lots of melanin. And so in the same animal, same conditions otherwise, you can try and isolate the effects of melanin. So he, in his studies, is also using the same raw PPG device that we're collecting data with, also using the same oximeters that we are using in the lab and in the real world study. And we're hoping to be able to put all of this together to try and gain some more insights. This is a slightly more controlled model. Obviously, a big caveat here, oximeters that were designed for humans were not designed to go on pigs, let alone pig ears or other body parts, form and fit. These are very important distinctions. So it is not by any means a perfect model, but we do hope there'll be some insights that come out of that. We've also been looking at or intrigued by proposals by different teams that are trying to address the issue of bias in skin pigment. Lots of new ideas for ways to approach this have come out. As part of the project, we have held a competition about a year ago. Of the dozen or so teams that applied, we selected 3 that are all undergoing testing in the hypoxia lab now to try and help give those teams data. research like this, we'll talk about a little bit more, but there are not that many labs that are able to do this. With the infrastructure we've been able to build up with open oximetry in our lab, we are able to do this more efficiently than we were before. And so we can add on device testing for groups like this that may not have access to this type of R&D capacity. And so we've been excited and fortunate to be able to do that. So now moving into regulation. We talked about some of these key issues with inadequate definitions of skin pigment, inadequate diversity overall, and also inadequate sample size overall for these studies. The current standards only require that these devices be tested in 10 humans in a controlled laboratory setting. It's becoming clearer and clearer that that is probably inadequate. Another thing to note is that a lot of the regulatory efforts are predominantly led by high-income country regulatory agencies. The FDA and the ISO have been doing incredible work to move as quickly as possible to try and improve standards, to try and elevate device performance. Also, want to highlight that the ISO group has also been taking efforts to try and diversify the membership, and by participating in the collaborative community, listening to more diverse voices that perhaps didn't always have a seat at the table for trying to influence standards moving forward. To talk about this a little bit, but there are not that many facilities in the world that do the independent validation testing that we do in San Francisco. In the US right now, there are only 2 labs that are independent labs that do device performance testing at academic centers. There's another lab that is a for-profit lab that also does a huge amount of great work. But most of these are based in predominantly lightly pigmented geographies. This is an inherent problem with the current regulatory, or is going to be an ongoing challenge as regulatory standards change, especially because there's going to be a huge increase in demand for the testing, which these labs are already struggling to meet demand. There is progress being made. Hopefully, we'll be hearing later today on some of the progress from ISO, FDA, and others. The Open Oximetry Project has been sharing data in real time with the regulatory agencies to try and help share insights into the things like power sample size calculations, to also provide input and data to guide rational decisions around the methods being chosen to ensure diversity of skin pigment. But all these things do have potential market implications. If we're talking about some of these anticipated updates, in particular, the larger study sizes, if these studies become 10 times bigger, our capacity to test in the lab, at San Francisco, for example, just put this in perspective, we have capacity to test about 3 to 4 devices per month. With the proposals that are on the table for changing regulatory standards, it may change such that we can only do 3 to 4 devices per year. And if you think about how few testing facilities there are in the world, this is going to be really problematic, especially if we're talking about new devices trying to come onto the market. Some manufacturers have in-house testing capacity. They do their own testing for regulatory purposes. But we do think there is an important role to be played by the independent testing labs, and we hope that there are more that will come online. Last thing that I'm going to talk about here has to do with this issue of how to disseminate the data on device performance, and also education for clinicians. Every device ships with fine print. Just like all fine print, nobody reads it. And more importantly, for pulse oximeters, by the time you have the pulse oximeter in hand, wherever that fine print was, it's long gone. You could take the effort to Google search and find the brochure and see the data for how that device performed, but there's not going to be any disclosure, by and large, on how it performed in people across different skin colors. And if you did find it in the documentation, just the gross accuracy, it's hard to understand this concept of root mean square error, the formula there in the bottom, or these the way that its bias is plotted and visualized. It's just hard to understand. Depending on how you're approaching this, if you're a researcher, maybe digging into that isn't as daunting, but for consumers, clinicians, people making procurement decisions or policy decisions, it's not easy to navigate the data or access the data. So that was part of the impetus for the website, which in the next couple of months will be undergoing some significant changes, including new data, but also new ways to communicate the data. For those of you, I think later on today, we'll go a little bit more into what's on the website and what's coming. So stay tuned for that. The other part of this data transparency and accessibility issue that we are trying to go after for researchers is how do we share the data that we're collecting in real time? So in the lab, we're collecting a lot of physiologic data. The project has allowed us to create an infrastructure that we just didn't have before. And we are asking some very specific questions, but there are a lot of other people out there that want to ask questions. We don't have access to this data. So we're sharing all of our data. So we've created a data repository that shares not just the reading from the pulse oximeter and the blood gas analyzer, but all of the real-time physiologic data throughout the study sessions from our real-world studies and our laboratory studies and everything. It's all going to be on there. There's about 120 patients that are in there. We'll be pushing another couple hundred patients in the coming months. So excited to be sharing that. Educational content is another area just as it relates to better communication on the issue of pulse oximetry. Many people have been working in this space. PATH has done a lot with pulse oximetry, Lifebox, WHO. I mean, everybody is doing tons of work in this space. There are some gaps that we have identified that we are hoping to fill, building off of the work that others have done. And this relates to the issue of variable performance in so much as trying to figure out how do we communicate better to clinicians that these devices are essential for patient safety, but they do have limitations. And just being more familiar with what those limitations are, especially when you're using the device to make clinical decisions, how can you buffer against these potential health and healthcare disparities that may relate to how the SpO2 is being implemented? Also, from a practical aspect, how do you use the devices in a way that increases the likelihood that you're getting an accurate reading? There is part of the project you'll hear a bit more about later that's working on a living infographic through the collaborative community. So wrapping up here, the preliminary findings, just a quick summary, we are seeing widely variable performance. It is not the case that we are tested 25 of the top devices and they all are showing a similar finding. We're seeing lots of variability. Not only variability, and we'll get into this in more detail later, not only variability across manufacturer or model, but from year to year of manufacture of the same model. We'll talk about, I think that's probably quite obvious why that's extremely problematic, but we'll get into that in a little bit. Similarly, the impact of skin pigment is variable. Same idea. We're trying to quantify how big of an effect there is, but it's different for every device. So what do you do with that? We need to figure out some of these other issues before we can dig deeper into understanding the root causes of skin pigment. But that is obviously still something that we are aiming for. We have made progress on trying to figure out how to better diversify the cohorts that these devices are validated in as relates to skin pigment. And not just us, but many groups have been working on that, and we're excited that regulatory agencies are going to be making some changes soon. We now have a better idea of how big the studies need to be. They need to be bigger. How big? There is still a little bit of a question mark there, but that's certainly something that has emerged. And these larger data sets we think are going to play a key role. We also have seen that our modeling for what our lab capacity and other lab capacities will be is just not going to be able to meet the demand. And so that is something that's very much at the forefront, is how to increase independent device testing capacity globally, especially in communities, geographies with predominantly darker skin populations. So upcoming stuff for this year, some of these education tools that I alluded to, the living infographic will be coming out in the next couple of months. Regulatory updates, I'll let the regulatory agencies speak to that, but what we hear is by the end of 2024, so that's good news. We will be continuing device testing capacity for the foreseeable future. With the infrastructure that we have augmented in the lab, we intend to be able to do some degree of OpenOx testing indefinitely, the amount of which will depend on a lot of factors. But we will be updating performance evaluations of all of our devices as soon as we have the new regulatory frameworks, or as soon as we have clearer data from our lab to guide what those study designs should be. Over the next couple of years, we hope that the open access data repositories will become much bigger, to a point where they'll be useful for our group and others to try and answer some of these more fundamental questions around the root causes of skin pigment. And then an ongoing issue is going to be how to balance all of this. The issue of access, cost, performance, patient safety, especially for low middle income countries. It's easy to imagine a scenario where regulatory changes take place, the cost of devices go up, access to devices that perform, ideally is limited, but the impact on patient safety could be profound. And so we're trying to figure out how to kind of not throw the baby out with the bathwater, so to speak. These devices, oximeters, are essential, even with their known limitations. They can be used safely. It doesn't mean there's not room for improvement, but without a balanced approach to this, we worry that there is potential market implications, especially for low middle income countries. So with that, I just want to thank the OpenOx team, some of the members here, especially Danny Chen here, who is our data analyst, who did a lot of work to try and get some of the data that we'll be sharing today together. So a big thanks to them and to our funders. I'll stop. Thank you.
Excellent. Thanks, Mike.
Thank you.
A lot of information. I think the big one, well, I don't know. I'll see. Are there any questions from the chat or from the group? If you'd like to ask a question, maybe raise your hand and we'll call on you. But in the room, while people formulate questions, any questions in the room? I can start. Yeah. Let's see. So I'll just get us started. So in your testing that you do in your lab, you mentioned that, well, you mentioned in regulatory testing, they do things to improve perfusion. In your testing, in your lab, do you do that? Or do you try to mimic real world?
Yeah, so it's a good question. To clarify, not everyone enhances the perfusion or things like that. It's just, it can be done and many do that. So it's not, I don't want to imply that everybody's doing that. For open oximetry testing for our cohorts, we do not by default warm the hands, for example, to try and improve perfusion. We measure the perfusion. It creates some challenges, which are around stability of the signal. It takes longer to reach a stable signal. It takes longer for, you could think of it as like a perfusion is less, the finger may take a little bit longer to equilibrate to the actual saturation of the body. It's an oversimplification of the model, but it takes us longer to do the studies. We end up with data that we have to throw out more commonly. There are reasons why warming is actually a nice way to do the studies in some regards, because it's a lot easier. But for OpenOx, we are not doing that. It just means it's harder to collect the data, but we hope that it will be more meaningful to try and answer some of these questions and better predict the real world performance, which is our ultimate goal.
Yeah.
But we still have a lot to try and figure out on that.
And the last point you made around the implications of changes to regulatory on low and middle income countries is kind of why we're here. I think there's an equity question, right? And this may be a terrible analogy, but in a way, it's like COVID with vaccines. If all the better, newer, more appropriate devices go to high income countries, what happens in low income countries? Do they end up with the less quality or higher costs so they can afford less? These are some of the questions we're trying to struggle with a little bit today, and I don't have the answer, unfortunately, but maybe this group does. So yeah, but I think that's something to highlight, is like when I can't sleep at night thinking about this, that's the question.
Maybe I can give a point on low-resource countries and countries where ICRC intervenes, and most of the organizations also intervenes, WHO, UNICEF. First, we rely on normative references. So we have the medical device ISO 13485 normative, and for the medical equipment, we have the ISO 9601. That's the baseline. So all organizations normally are working through those normative references. The second normative streamline and domain is WHO and the medical activities, medical and UNICEF, all the publications, all recommendations. I give you an example. We have changed the standard of blood bank. So immediately we refer to WHO in terms of normative way with gas, etc., and also in terms of handling guidelines, because there is a wide. So that's the way it is done. And then we translate this, the domain, into the public domain and the commercial domain. So we rely on suppliers with the narrative they want to provide to all organizations, the specification we use, and then we try to translate this into the reality with facilities, health facilities we support. So there are health facilities where we intervene as an actor. So, as you know, we open ICRC hospital in Rafah, field hospital. So we have our own staff. So there we can monitor carefully what we use, etc. And we have, in most of cases, like most organizations, facilities where we are not there. We do sporadic support, and then it's extremely difficult to monitor the use, the performance, and sometimes we support the 1 year, 2 years, and then we withdraw. And we don't know what's going on.
What happens?
So this is the reality of the field, and this is where we work. So I hope it helps you to I would say, imagine what's going on.
Yeah.
But at least if you have those normative steps in place, plus confidence with a manufacturer, supplier, qualified, that's already something. But as far as I know, on this problematic of skin color versus performance of oximetry, there is not much communication on that.
Right.
First, on the WHO recommendation. And second, on the manufacturer side, there is nothing. Yeah. Nobody communicates on this. And as you mentioned, on the COVID side, there's been a massive demand of oximeter worldwide because of it was in the diagnostic, one of the, so many organizations, I mean, it's a bit like when you have pandemic, or you have cholera, or you have, when you have a big demand like this, so you use what you found on the market. And I'm sure many organizations have used not appropriate technology, and it ends up with this kind of, apart from what you presented, but with a problem in diagnostics, identification, and performance, for sure. Yes. Yeah. But that's the problem. We had a recall recently on the oximeter with a trademark that I will not talk about. So those products were distributed in Ukraine, in Syria, in different facilities. But it is a challenge to address and to replace and to track, and because, as I said, organizations are not often there on permanent basis. But it's our duty to address this, and so we do what we can, but it's a challenge. So this is what I wanted to bring.
That's helpful.
Thank you. Yeah.
So you rely on the standards provided by ISO, WHO.
Yeah. That's the reference. Yes. Felicity, I know you are with us. Maybe you want to add something? You are on mute, Felicity. She's there. She's our doctor in charge of the hospital facility. But
Felicity, jump in if you want. I see Patrick has his hand raised. Patrick, please.
All right. Thank you so much. Let me probably just state my background. Actually, working with building a special capacity for use of oxygen on the African continent. So I'm a technical officer within the Africa CDC. At the peak of COVID-19, actually, I did coordinate distribution of medical equipments to member states, and those actually included oxygen concentrators, mechanical ventilators, as well as Pulse Oximeters. We also did ensure that, we did, with partners, ensure that, some of the oxygen plants and were either renovated or others actually were ambitious to set up new ones. On the African perspective, really, at the peak of COVID, I think we saw a significant need for Pulse Oximeters, and especially at the community level. I think this is where we had quite a lot of issues. And I think also borders on issues of equity in terms of availability and access to this important tool in primary healthcare setting. So that's the biggest challenge that I think we have on the African continent. So that's one area that we need to address also. As we are talking about functionality of these Pulse oximeters, especially for people with darker skin tones, we also need to also look at issues of equity in terms of how available are these tools, because definitely they're on demand and they're actually needed. Apart from COVID, of course, we have quite a lot of chronic illness that require that monitoring. We have quite a significant prevalence of pneumonia, for instance, in children, in babies, and that comes to play. And then realize that some of our PHCs, the primary care facilities, actually don't have those tools. If they have the tools, then one of the issues that we need probably to look at is issues of training, capacity building among healthcare workers, capacity building among community healthcare workers. To ensure that they have that understanding of the use of these Pulse oximeters, and I think that is also one of the biggest gap that also need to be looked at. We also, I think, need to also really look at these Pulse oximeters, for instance, for me, really, and my experience, actually, I'm a medical doctor by profession, and that's my background actually before getting into this public health journey. But one of the things that you do realize is we don't talk much about the usability of the Pulse oximeters, because we believe that any standard Pulse oximeter that is available for use, how can it can provide the same readings for people even with darker tones. But I think from the presentation it's clear that we have some inaccurate readings because of that complexity. And I think those are things that we need our clinicians especially to be aware of, and actually prioritize this in some of the training. So you read actually hear about this component. So I think the message should really be clear. Then the other part again is looking at this good presentation that was given. The aspect of research is based more in high-income countries, and then of course it will be difficult really to tailor that or the findings to especially 1.3 billion people that are based in Africa, if these actually designed at that stage. So I think we need quite some kind of robust research, and Africa CDC actually is on the table to collaborate on such aspects. We have the Partnership for Harmonized Manufacturing of Health Products on the continent, I think formerly known as the Partnership for Vaccine Manufacturing. So that is, one aspect that, Africa CDC is actually pushing various partners to ensure that, we have such kind of, either technology transfer of industries actually producing these, medical products, medical equipment actually on the African continent. So that's one big component. And of course, to do that, we need some kind of data, on the African continent to really understand, aspects of, the usability of these pulse oximeters that are usually imported, from outside the African continent. So, so I just wanted to state a few reflections on that. So otherwise, thank you for that great presentations and other reflections from our colleagues on the call. Thank you, and over.
Thank you, Patrick. Yeah, there was a lot in there, but I think you had mentioned the training capacity building. I think that comes back to guidance from the normative bodies that would be useful, which comes back to Mike, which is pointing to, are there ways to mitigate this either through training? Maybe, I know pulse oximeters are more useful when you're looking at a trend versus a spot read. So maybe that's something that guidance could portray. But also I know guidance when it comes from WHO has to be simple and straightforward, and it can't be too nuanced. Otherwise it sort of loses its impact. I know we're over time. Andrea, don't kill me. I think Yasser, you had one thing to say, and then we'll move on.
Yeah. Thank you very much, Mike. Good work and excellent presentation. Just 2-3 quick questions about the laboratory studies regarding pediatrics. Is it, we have seen that there are many devices which is on the green side also. Is it across the board, all the age groups, or is it only in the pediatric group or the older group, or something like a population which is more towards in the green side? Secondly, you mentioned that it's a 4% where you put it. Is it a 4% point or it's a 4% of the reading? I'm not sure about that. Thirdly, there are other factors which affect the reading of pulse oximetry, such as nutritional status or anemia, blah, blah. So I know you mentioned it that you try to adjust for a few of these. Have you adjusted all of these? Because lastly, the dark skin is quite a qualitative statement, like for a health worker who is actually using the device. It's quite difficult for him or her to say, this is not, this is like. So do we have something? I have seen in one of your slides, but do we have something reliable when we say, from here onward, this is a programmatic, but before that, it is not. So it's a few thoughts only. I know it's, if you can let me know some of them, that would be helpful.
Yeah, those are all great questions. I'll try and chip away at them. So in terms of the studies that we do in the lab, it's adults only. And that just has to do with pragmatic aspects of being able to do this type of study. It's invasive. We have to put in an arterial line. We are lowering oxygen saturation, things that are just not feasible with children or ethical in some ways. And so we don't. There's pediatrics, then there's neonates.
Yeah.
And so what you're talking about is a device that was really tested and validated mostly in adults. There are some validations that are done in pediatrics and neonates in the hospital setting, but those are limited. You're not controlling anything, you're just observing and useful. And we do some of those studies, but we're not right now as part of OpenOx doing that. The team at Stanford is doing a study in pediatric patients, and there are 2 other teams within the Collaborative Community Clinical Trials Network that are doing pediatric studies in the real world. There's not a lot of good data for kids. It's the unfortunate reality. And so, most of what we're talking about, big caveats in the adult population, choose whatever multiplier you want for the caveats that then apply for kids. In terms of the 4% that I was showing, that's something called root mean square error. Okay. It's like I'm not a statistician. Thank God I have really smart people that I work with who can deal with this stuff. But you can kind of think of it as combining precision and accuracy into one variable. Really simplified, you can almost think of it as like plus minus that amount of the SpO2. So if something's reading 90%,
Yeah.
then most of the time it's going to be within 4% of that. It doesn't really mean that, but it's like pretty close to that. Yeah, and then your last point about, if I understood correctly, kind of two parts of it was like not accounting for all covariables.
Yeah.
100% agree. There are a number of things that could be at play here. There are easily a dozen hypotheses as to what may be contributing, what may be interacting. And if we're only doing the testing in San Francisco, and Colorado, we're missing a huge number of variables that we may not have even known to look for. And so again, I think that's why, one of the reasons why we're very interested to try and do testing in other places and partner with other teams in other places. To your point about a community health worker or just anybody who's using a device, when should they be concerned? I think that there are scales that can be helpful for that. The bigger problem is that it's so different by device. So if you say, be concerned if your patient is this light or this dark, specific to a device. And in one device, it may be overestimating. In another device, it may be underestimating. There's so many caveats to that, that a simplified rule of, well, in all patients who are dark, just assume that it's much higher. I don't think we're there yet in terms of that. But what I do think is, potentially useful is in guidelines, more awareness that this is a very useful but imperfect number. In the same way that you would not assume a blood pressure reading from a blood pressure machine, if it was different by 1 or 5 points, if you're making a clinical decision about that, you would not use it in that way. Pulse Ox people have come to assume that it's perfect. And it's not. It's just like most everything else. It has to be used in context. And so if anything comes out of this, I think that the more practical approach may not be, okay, with the device in front of me, does it overestimate, underestimate? What do I do with dark or light? It's going to be, this is a useful tool, but it's one piece of information, and I'm not going to decide care based on it alone. And that, I think, would be a big step forward. I hope that answered.
No, thank you so much. Thank you so much. Because I have similar point of view that Pulse Oximeter is a wonderful device, but you cannot rely each and every time only on Pulse Oximeter. There are many other factors to consider for the CMI. Thank you.
Thank you.
Julie, do we have time? We're over.
Yes, we're over.
Freddie, I know you
15, nearly 15
Okay.
minutes, but do ask.
Okay, you have clearance from the plan.
No, thanks. Mine is not a question. I think one of the messages I draw from the presentation and the discussion is the importance of emphasizing post-market surveillance, given so the implementation, but also thinking about, because we know from economics, supply and demand. I'm pretty sure when demand reaches a certain level, then costs eventually need to come down. So thinking about the pathway to models that eventually lead to that critical demand that eventually offsets all the cost implications of all these important interventions.
So increasing the demand to help manufacturers get a higher level of production, so their prices come down. Yeah, I think, there's pool procurement mechanisms that could be like UNICEF. Okay, that's a good comment.
You have one point also for going into the international organization market versus suppliers. What we are struggling for this kind of device is the origin of the product. So there is a lot of issues with the sanctions, US sanctions all over the world. And many suppliers, they sometimes even refuse to say, well, this product is supposed to be sent in Syria or in Libya or whatsoever, in Iraq, and they don't embark into the business. They say, no, we refuse. So we have this with big lab manufacturer, especially with link with US origin, and also all those equipments. So even though we have a derogation with OFAC, with, you know, federal authorities and things, but that's really it's a nightmare. I'm handling few files at the moment, I tell you, it's a nightmare. And we are blocked. So we try to find alternatives in Asia and things, but still it's a big constraint. So apart from the technicalities, this aspect is going to be a blocking point for all organizations.
It's another.
Unfortunately, it's not the critics, but the USD is not the money of business, it's going to be a money of sanctions. So that's a problem. No.
That's
a
another
problem.
complication I had
Yes.
not
Yeah, but it's a
layered
reality.
on.
That's a reality.
Is the sanctions.
It's sad, but it's like this.
Yeah. Okay, noted. I think we'll go to the next session. And I'm gonna look at it, describe what that is.